This is problem 3-125. It's on page 145. A 0.2 liter glass of water at 20 degrees Celsius is to be cooled with ice to 5 degrees Celsius. Determine how much ice needs to be added to the water in grams if the ice is at A, 0 degrees Celsius, and B, negative 8 degrees Celsius. Also determine how much water would be needed if the cooling is to be done with cold water at 0 degrees Celsius. The melting temperature and the heat of fusion of ice at atmospheric pressure are 0 degrees Celsius and 333.7 kilojoules per kilogram respectively, and the density of water is 1 kilogram per liter. That was quite a bit of information, so let's write down what was given and we'll sketch the system. The system varies from part to part, so I'll just sketch the system with the ice cubes in it, realizing that in what is essentially part C, those ice cubes are not there, there's just water. But the point is we just want to cool down this drink to some final temperature. So the water begins at a temperature of 20 degrees Celsius, and we have to move that water to a final temperature of 5 degrees Celsius. Okay, so we want to find the mass of ice required if the coolant is A, or mass of coolant required. If at first we have ice at 0 degrees Celsius, which would be defined as the initial temperature of the coolant or the initial temperature of the ice, or if we had ice instead at negative 8 degrees Celsius, which I will define as T sub I, temperature of the ice. Or C, if we had just water at 0 degrees Celsius. Now, what's the key difference between these? Well, there's a couple of key differences. First of all, if we just have water that we're adding and the water's cooler than what we're trying to cool down, well, we can add enough water where finally we end up at 5 degrees Celsius. But notice that's just a sensible change in the coolant. All that the coolant is doing there is changing its energy, or its temperature, or its sensible energy. If we had ice at 0 degrees Celsius, then what would happen? Well, the ice would be in the solid form. It would be in the phase of solid. So it would have to melt. It would have to go from solid to liquid, and then its temperature would have to go from 0 degrees Celsius to 5 degrees Celsius and be in equilibrium at the end with the drink, whatever that is. Now we're told that it's water, but this could be tea, this could be Coke. It really doesn't matter. The main component of even a drink such as milk is water. That's the main component of mass that's in the drink. Now, if we had ice at negative 8 degrees Celsius, then something interesting would happen. The ice would actually have to come up to 0 degrees Celsius before it could even melt at all. Then it would have to melt from 0 degrees solid to 0 degrees liquid, and then its temperature would go up to 5 degrees Celsius. So the part B is going to be the longest, most effective. So we would expect really that part B would give us the smallest mass of coolant required. Part A would be more mass, but not as much as C. C would be the most mass required. So let's see. What I'm going to do is write down an energy balance. Q minus W equals delta U. And the system that I'm going to take will include both the water, or the drink that is to be cooled, and the coolant. Most of the time, this is ice. Sometimes it's just liquid water at 0 degrees Celsius. So since my system consists of the drink and the coolant, I'm going to assume there's no heat transfer across the system boundary. Now, there will be heat transfer, obviously, from the drink to the coolant, whatever the coolant may be. But that's not heat transfer across the system boundary. Now, we could stir it a little bit to increase and enhance the convective heat transfer, but that amount of work is going to be small, so we'll neglect it. So both these are 0, and the change in internal energy of the system will just be equal to 0. Now that change in internal energy will consist of the change in internal energy of the, let's say, drink, and the change in internal energy of the coolant. Because obviously the drink's internal energy is going to drop, the coolant's internal energy is going to rise. So that should make sense. Now, let's apply this to the case where we have ice, since we have that in two of the cases. So the mass of the drink or the water, let me just switch and call the drink water because that's what the author said. The mass of the water times the heat capacity of the water times the final temperature of the water less the initial temperature of the water. Notice we've got the initial temperature of the water here. We'll just put the water inside. This is just H2O. And we've got the final water temperature here, which is just 5 degrees Celsius. These two things are just numbers. And oh, by the way, we've got a volume of 0.2 liters, which if you look at it and look at the density they gave us, that tells us that the mass of the water, since it's just 1 kilogram per liter, the mass then is just 0.2 kilograms of drink or water that we're trying to cool. So that's an easy part, that's not a big deal. So plus the mass of the ice times the heat capacity of water. Now why am I doing this? Well, this part that I'm about to write, what I'm doing is I'm accounting for the change in the internal energy of the ice as the ice changes temperature. So this is the ice in the liquid phase, so it should really just be the mass of the coolant, times the heat capacity times the temperature change, because it has to go from the initial temperature of the ice, whatever that may be, to the final temperature of the water. So the ice, after it melts, understand, is going to change temperature from 0 degrees to 5 degrees, and that's what this piece is taking care of. So this is the sensible energy change of the coolant. Okay? The last piece is the latent change. In other words, the phase change. Let me put the 0 on this side because I'm out of space. I hope this is on in the video screen, but it's just a lambda. And what it says is that this term here accounts for the latent energy change of the coolant. Okay, so because the ice melts, we're going to absorb a certain amount of energy. Because that melted ice changes temperature, we'll absorb even more energy from the water or the drink or whatever you want to call it. Okay, so basically, notice we've got mass of ice here and mass of ice here. Why do I have mass of ice here where we're talking about latent energy change? Well, that makes sense. It's ice going from solid to liquid, okay? Why do I have mass here of ice? Well, after the ice melts and it becomes liquid, it's still the same mass. So I can use it here as well to model what happens once that ice that's melted changes temperatures. So it's the same mass, it's true that in this case it isn't ice, in this case it's actually liquid, but it started off as ice, and so that's why I've got it written here. So solving for the mass of the ice that's required, what you find is that you've got the mass of the drink or the water times the heat capacity of the water multiplied by the notes here, multiplied by the water's initial temperature less the water's final temperature, divided by the heat capacity of water, because remember the ice is just water itself, times the final temperature of the water less the initial temperature of the ice plus lambda. So all I've done is I've combined these two terms, factored out the mass of ice, moved things around, and there we have it. So once again, this piece is due to the sensible change. This is where the ice goes from 0 degrees, for example, in part A, liquid, to 5 degrees, which is the final temperature of the drink, plus the lambda, the latent heat capacity, or not the latent heat capacity, but the latent energy change. So let's plug in the unit, or plug in the numbers. We've got 0.2 kilograms. The heat capacity of water, let's see, it would almost cancel out except we don't have it here. So I'll go ahead and plug it in. 4.19 kilojoules per kilogram per Kelvin. Let's see, times the initial temperature of the water, 20 degrees, less the final temperature of the water, 5 degrees Celsius. Now notice this, what's in the numerator is just talking about the drink and how the drink changes its energy, it loses energy. Okay, so divided by the heat capacity of water, 4.19, kilojoules per kilogram per Kelvin times the temperature change. Well, the temperature change of the ice, it goes to 5 degrees from 0 degrees. Because remember, the ice begins at 0 degrees Celsius. It changes phase, and then it's still liquid at 0 degrees. Okay, so it starts off at solid, 0 degrees, goes to liquid at 0 degrees, and then comes up to 5 degrees to be in equilibrium with the drink. Okay, so this takes care of this piece here, this denominator piece. But then we have to add on to that the latent heat of fusion of the ice. In other words, it takes some energy to melt the ice in the first place. And that amount was given. I didn't jot it down, I did read it off, but it was 333.7 kilojoules per kilogram. And that's the amount of energy required to melt the ice. Now, what you should do, you should pause the video at this point and compare the magnitude of this term to the magnitude of this term. Okay, so calculate 4.19 times 5, essentially, and compare that to 333.7. Now, hopefully you pause the video and you come back. I'm going to do some back of the envelope calculations and say 4 or so times 5 is about 20. So this is a little bit larger than 20, but this is about 300. So this is an order of magnitude bigger than this. So where does most of the cooling come from? It comes from melting the ice. That's where most of the cooling of the drink comes from. There's a small contribution here, but it's not very large. Okay. Anyway, plugging all that in, you find that the mass of ice required, looks like mice, but it's not. It's the mass of ice is about 35 grams. Let me just put a G there. Grams. Okay. I'll separate my results and my givens from my calculations. Okay, well that's interesting. Well, what if the ice begins lower than the freezing point of water? What if it begins below 0 degrees at -8 degrees Celsius? In fact, if you take ice out of your freezer, you will find that that ice is subcooled. It's below its melting temperature. So this is a little bit more realistic. Now, it should require a little bit less ice, right? Or maybe a lot less ice, because not only will we have the sensible energy change from 0 degrees liquid to 5 degrees liquid, and we'll have, again, still the latent change from solid to liquid, but also there will be a sensible change from ice solid at -8 degrees Celsius to ice solid at 0 degrees Celsius. So this is going to happen before either one of these two can happen. In fact, if you were to write out the energy balance, you just have one more term on the ice. And that term would basically just be a plus mass of ice, heat capacity of ice, and you have to be careful because the heat capacity of ice is different than the heat capacity of water, times the initial temperature of the ice. Now notice the ice begins at -8 degrees Celsius, but it ends at 0 degrees Celsius, so unless it's initial temperature. So this change here is from -8 degrees up to 0 degrees. So this would just be one more term in our energy balance. Okay, so then what would that do? Well, that would just add one more term to the denominator of the mass that's required. So it's going to reduce the mass of the ice required because it's going to make the denominator bigger. And that term would simply be the heat capacity of the ice multiplied by the temperature change of the ice. Now remember, once again, the ice goes from -8 degrees up to 0 degrees. Okay, so this term overall will be a positive term, and it will decrease the mass of ice required. So if we add that in, it turns out the heat capacity of ice is about 2.11 kilojoules per kilogram per Kelvin. And the change in temperature of the ice, if you plug in 0 here and subtract a -8, you'll just get an 8 degrees Celsius change. Now hopefully that's not off the video, and if it is, you can see I'm pointing to 8 degrees Celsius down here and change times 2.11 kilojoules per kilogram. Once again, let's look at our order of magnitude estimate. The first term is about 20 or so. The next term is about 300. What is 2 times 8? Well, that's about 16. So that really doesn't add a whole lot to the cooling capacity of the ice. Cooling down the ice below 0 degrees really doesn't do a whole lot. It doesn't help much. So if we throw that into the mix, though, what you find is that the mass of ice required, if the ice is subcooled, let's see, just plug in all these numbers in, you'll find that the mass of ice required is 33.8 grams. So it is slightly less, but notice that's not a huge difference from 35 grams. So the subcooling of the ice really doesn't make a whole lot of difference, but there is still yet another scenario. What if we just start with water at 0 degrees? Well, then what happens? Well, then we're not going to melt any ice. We're certainly not going to heat up the ice to its melting point. So all that happens to the energy balance is that we lose the latent change of the ice, which is, notice the biggest piece down here, and we lose the sensible change in bringing the ice up to the melting point. Basically, we've just gotten rid of a lot of the denominator. Now this looks like a really bad idea, because essentially what we've done is we've gotten rid of a huge piece, and a piece that really didn't matter, right? And so now the mass, this would no longer be mass of ice required, because it never was ice. Now it would be mass of cooling water. Let me just call that coolant to distinguish it from the drink, which I've called water. Okay? And we see this is a really bad idea, right? The latent heat of a fusion of the ice contributed a significant term to the denominator, but now that's gone. So if you calculate the mass of water required, you'll find here that the mass of water, let's say coolant, you'll find that it is 600 grams to keep the same units. Well, that's 20 times the amount of ice required. It's not really surprising, because remember, this denominator went from about 300 or so to about 20. And so that's a huge change. So how much water is this? Well, if you look at the density of water, the volume of cold water required, since the water is about a kilogram per liter, then the volume required is about 0.6 liters. Now we started off with a drink that is 0.2 liters and added 0.6 liters of water to it. Now, remember I said that if this is milk, or if this is Coke, or if this is tea, it's mainly water, and so this analysis is valid for any of those. So if someone came along and said, you know what, ice is just a very irresponsible thing to do, we should never make ice because it's a bad idea, we're going to cool your drinks with cold water instead. You see how much cold water would be required? It's a whole lot more cold water than just the solid ice. Okay? Now another trick here, if you're interested in drinking tea and you like drinking tea and you don't like the ice watered down, I mean, after I look at this, 0.6 liters versus 0.2 liters, you'd be watering your tea down like crazy, right? It wouldn't make any sense. It wouldn't be tea anymore, it'd be just impure water is all it would really be, right? So if you're interested in cooling down your tea, there's a clever idea out there. If you make your own ice cubes, just pour tea into the ice cube trays, let it solidify, and then use tea ice cubes to cool your tea, which will be quite effective. So there's the solution to problem 125.